So our final example, we're going to take a look at how do we go through and reverse the order of integration for one more of these double integrals. Clearly, we have a cos x squared. Cos x squared is a non-evaluable integral in terms of x. So what we did before is we started by plotting the region. Okay, so what we have initially is we have that x is equal to y squared, and we also have x is equal to 9. Okay, those are our upper and lower bounds. If we solve this, we have root x is equal to y, and then obviously we still have x equals 9. So let's plot the region, and then let's turn this from a type 2 to a type 1 double integral. Square root of 9, very easy, looks like this. X equals 9 looks like this. All right, so this is y equals root x, and then we have x equals 9. And what we'd like to do is we'd like to just go up and down to make this into a type 1 integral. Hopefully, when you work through the problem, you are able to see that the lower bounds for y now range from 0 to root x. The lower and upper bounds for x range from 0 on the left-hand side all the way over to 9. So that's our domain D that we're looking for the general region. We can now set up a double integral. Our double integral is going to be integral 0 to 9, always the numeric evaluation on the end, at the end, 0 to root x. We still have the original integrand y cos x squared. However, now we're reversing the order of integration where we're going up and down first, so that's dy, and then dx, which is the change from 0 to 9. At this point, we evaluate y, keeping cos x squared a constant. This is very easy at this point because y has nothing else along with it. So we're going to get the integral from 0 to 9 of y squared over 2, ranging from 0 to root x cos x squared. We still have that dx on the outside. We still have that cos x squared, but it's not that big of a deal. We're going to substitute root x and 0. So now we get integral 0 to 9. Substitute, we have root x squared over 2 minus 0 squared over 2. We have cos x squared, and we have our dx. Right? Simplifying what's inside of the brackets, we know that 0 squared over 2 is nothing, so this just goes away. And then square root of x squared is just going to be x. So one of two ways that we could write it. We could write it as integral from 0 to 9 of x over 2 cos x squared dx, or we could factor the 1/2 out, and then we would be left with 1/2 integral 0 to 9 of x cos x squared dx. Fortunately, we're left with an evaluable integral now. We can utilize our u substitution technique. We're going to say that u is going to be equal to the interior composite function of x squared du 2x dx, and then finally du over 2 is going to be equal to x dx. All right, so now we can perform our u substitution. I'm just taking a look at a previous really quickly. I may have forgotten the dx. I did not. Good. So by substitution, we get 1/2 integral a to b. Instead of x dx, we're going to replace that with du over 2. And then we're going to have, instead of cos x squared, that's just going to be cos u. We don't need the du, we already have it. We're going to now integrate. I'm also going to factor out that 2. So we're going to get 1/4. Antiderivative of cosine u is going to be positive sine u. So we're going to end up with sine of u, ranging from a to b, which is the same as now 1/4 sine of x squared. Limits of integration 0 to 9. Finally, we substitute 1/4 sine 9 squared minus 1/4 sine 0 squared. We know that sine of 0 is 0. 1/4 times 0 is 0, so this term goes away, and we're just left with a really nice answer of 1/4 sine of 81. We're going to leave it as is. We don't want to get the approximation. We always want to try to give the answer in exact terms. All right. If you were to put this as an approximation, remember 81 is a radian measure. So don't forget, in real life, if you're ever trying to utilize the sign of any function with a number inside of it, don't assume it's degrees, always assume it's radians unless otherwise specified.